All right, let's put all this together now and see what we can get out of this and go from there. So, I want to take a resistor, an inductor, and a capacitor, put them in series, connect them to a source potential that is alternating sinusoidally. We'll have ourselves a delta V of T. We've got ourselves a resistor, an inductor, and a capacitor. And what do we want to know? Well, generally everything, but it'd be nice to know, hey, things like, what's the maximum current in this circuit? RLC, source potential here. So, as you can imagine, we could go through Kirchhoff's laws, do a little loop roll here, start putting stuff all together, but we've done it all separately already. And because we're sticking these in series, and the way that their phase behaviors acted, and is the way that they responded with the source potential itself in terms of their currents, we just stick it together and make the correlation directly from that. So, at any given moment in time, the current everywhere in the circuit has to be the same, right? We can't have the current is out of phase with the current here is out of phase with the current over here. That doesn't work. The current's the same everywhere. The total source potential itself has to be one value at any one given moment in time as it fluctuates. But that source potential itself gets broken up across these three different elements that have different correlations through time itself. So we'll sort of switch how we're going to look at this, and we're going to draw this out with Phasor diagrams and then extract out some information with this. So individual Phasor diagrams. This we had for the resistor. For the resistor, we had, here's this, at some time, we'll just say at t equals 0, we had that the current is along here, and the potential difference is also along here. That's delta V sub R. That's the potential difference across the resistor, not the source potential anymore. Because again, now it gets split up. They weren't equivalent, or they're not equivalent anymore. So this is delta V sub R. The projection of those onto the axis would give their instantaneous values great. Come over here, we've got ourselves the inductor, and draw it out. Again, we're going to put the current in the same orientation here. So we're starting them all the same. There's I max. And we had that the current lagged the potential difference in the case of the inductor. Lagged, right? Minus pi over 2. So in this case, the current's behind. That means that the potential difference across the inductor is ahead. So we've got this. This is delta V sub L. Again, it's projection onto the y-axis, gives the instantaneous value for that. And then we've got the capacitor. And same sort of scenario here. With the current in the same orientation. I max. And in this case, we have that the current led the potential difference. Here's the potential difference. Make that a little bit different. Potential difference across the capacitor. Delta V sub C. And current led the source potential, led the potential difference for the capacitor. And in all of these cases, everything rotates around at a constant angular rate of omega. And that's it. So what happens if we combine all these? Well, the currents in the same orientation with all of these. Great, because in the circuit, the current should be the same everywhere. So combined. What do we have combined? A little bit bigger. We've got ourselves current. We've got ourselves potential difference across the resistor, delta V sub R. We've got ourselves the potential difference across the inductor, delta V sub L, and we've got ourselves the potential difference across the capacitor, delta V sub C. At any given moment in time, the projections of all these onto the y-axis have to add up to be equal to, same as the source potential. Well, what happens if we did something else? And if we just looked at the overall aspect of how these three add together? So what I want to do is take these two and note that one's positive while one's negative. As the projections on the y-axis are concerned, one of them subtracts off the other. So I'm going to rewrite this one as this. Have ourselves, we already know the current's going to be in that orientation, so I'm just going to draw out the potentials right here. Here's delta V sub R, and then we've got this, which will be delta V sub L minus delta V sub C. The difference between those two values in terms of absolute values in this case. So take this, subtract it off of that, and it's kind of like add, but nonetheless, now we've got those two. Well, we've got the currents like this. What about the source potential? Source potential has to be the sum of these two. Not the sum of projections, but the sum of those in terms of x and y components. So with this, we've got this going on. This little triangle here, we've got this. That has to be delta V max, source potential. Right now, its projection onto the axis here would just give us the difference between delta V sub L and delta V sub C. But again, this all rotates at the same rate, and what we end up getting for this sort of configuration here, the way that it's drawn out, would be this. Got ourselves it's going to get a little confused, but that's okay. Come back here, got ourselves I max, and then we've got ourselves delta V max. Their projections onto the y-axis give the instantaneous values of what they are. Both rotate around at some constant angle or rate omega, and then there's this angle between them, this phase angle, which is ultimately going to depend on this right here, delta V sub L and delta V sub C, how big it is. And this tells us by what amount the potential difference leads or lags the current. That's what this phase angle is, phi. So, what can we do with all of this? Well, we'll go back to a couple things that we wrote down before. First off, we had that chi sub L was equal to omega L. Chi sub C was equal to 1 over omega C. We've got from this distinction right here that delta V sub R plus, let's do this. This is like the hypotenuse of this triangle, right? So we've got a delta V sub R, and then we've got a delta V sub L minus delta V sub C here. So we have to have that delta V max is equal to the square root of delta V sub R plus delta V sub R squared, plus delta V sub L minus delta V sub C quantity squared. So just getting triangulation here, hypotenuse of that nice little right triangle that pops out from those values. And this is what we get for the maximum source potential has to be equivalent to this. And then we've got things like delta V sub R is equal to I. These are all max values. Max. This isn't time varying anymore. Max value, these are all in terms of max values. So we've got I max times R. We've got the delta V sub L is equal to I max times chi sub L. And delta V sub C is equal to I max times chi sub C. Where again, chi sub L and chi sub C are defined in those ways right there. So what happens when we start sticking this all in here? We're going to have a common term of I max that can be factored out of this squared, factored out of that is squared, and pulled on out. So this can be written as delta V max is equal to I max times the square root of now R squared plus chi sub L minus chi sub C quantity squared. Chi sub L minus chi sub C quantity squared. The I max just gets factored out, and there we go. This right here, this is a nice, interesting quantity. We're going to call that something because ultimately it's overall this, the resistance, the inductive reactance, and the capacitive reactance, which dictate what sort of maximum current we get for a certain maximum potential difference. We define Z is equal to square root of R squared plus chi sub L minus chi sub C quantity squared, where C is equal to what we call the impedance. That's an A there. I might be spelling this a little bit off. Impedance, P-A-D-A-C. Impedance. So, what do we have? The impedance has units of ohms. Oops. Because, what do we have? We've got the ability now to write delta V max is equal to I max times Z, which is like Ohm's law for an AC RLC circuit. So, to be honest, in general, we're not really concerned about, hey, what's the instantaneous potential difference across the resistor, across the inductor, across the capacitor. It's more about, hey, what's the maximum current that's allowable in the circuit? Maximum RMS current, maximum, what's the impedance of the circuit? How do we maximize or minimize the impedance? Things like that. But all this other stuff that we've been doing sort of leads up to this right here. Leads up to that. The impedance controls the maximum current in this AC circuit, the overall impedance. And that could just be, if it's purely resistive, the impedance could be equivalent to the resistance. But generally, we stick in some other elements, there's some sort of inductance, some sort of capacitance. Here we go. That's a great couple last things with the impedance of the circuit is, when is the impedance minimum such current is maximized. How do we get the maximum current? Well, we start looking back at this right here. How do we get the smallest Z possible for a given inductor, capacitor, and a resistor? So I'll put this in for a given R, L, and C. Well, Z is its minimum. So when chi L minus chi C is equal to 0. That's it. If chi L minus chi C is non-zero, even if it's negative, doesn't matter. If it's non-zero, you'll have that Z is going to be greater than just R. But we can still have an inductor and a capacitor and a resistor in the circuit and get it so chi L minus chi C is equal to 0. And for that, we will get the maximum current because we will have minimized the impedance of the circuit. So how do we do that? Well, again, we come back up to what is chi L and what is chi C. Ultimately, from this, that will happen when chi L is equal to chi C, which says that omega L is equal to 1 over omega C. And what can we do with this? We solve this out. Omega is equal to 1 over the square root of LC. This is the resonant frequency of the circuit. The frequency that it can be driven at, the frequency of the source potential, if you will, that will give us chi L minus chi C being equal to 0, such that we will have the maximum current in the circuit. And that's fantastic. One last little thing with this, besides that resonant frequency, is getting the phase angle between the potential difference in the current, getting this phi right here. So if we come back to this, we've got I max, we've got delta V max, and ultimately I max is always in a certain orientation, same orientation as delta V sub R, right? So if we come back to this right here and get this correlation, look at this in particular, we can get that this angle right here, this phase angle phi, is going to be gotten by looking at the tangent of opposite over adjacent. Tangent of theta is defined as that. Go like this. The tangent phi, is equal to delta V sub L minus delta V sub C divided by delta V sub R. But again, all of these can be rewritten in terms of I max R, I max chi L, I max chi C, and we get that this is equivalent to this chi sub L minus chi sub C. This is always a challenge for me. That's a C, that's a nice L, divided by R. So all said, the phase angle between the potential difference of the source and the current is arctangent of chi L minus chi C divided by R. Turns out to be positive. Well, that means that the potential difference leads the current, or that the current lags the potential difference. Turns out to be negative. Well, negative would mean that the potential difference is under the current, and thus the current would lead the potential difference. And really, what does that depend on? It depends on these right here. If chi L is greater than chi C, you get positive. Chi L is less than chi C, you get something that's negative. And that depends on the individual inductors and the individual, or not individual, but the overall driven frequency of the source potential. Whew. Good times. Good times indeed. And yeah, that's that for right now. Whew. AC circuitry, 1, 2, 3. Take care.